This is a set of data that we've actually already looked at way back in chapter 3 days. So how many iPhones will be sold if we're using the year and the units sold as our variables, okay? This is the data we looked at. Here's the scatter plot. Here's the residual plot and the summary statistics on it. All right, knowing what you know right now, would you say that the linear model is the appropriate model for this data? No, why? It's curved where? There's curvature here, and there's also a curvature in our residual, right? There's a pattern. So good. Would we say the linear model for this data? No. The scatter plot is curved. And there is a leftover pattern in the residual plot. Also want to bring your attention to the R squared value in the table. Look, it's only 91%. Okay, it's all right. It's not horrible. It's not close to 100. I mean, it's not super close to 100, right? So, now, let's jog your memory, see what you remember from Algebra 2. If I did draw a line here, what parent function does it most likely fit? Exponential. Do you remember exponential functions, guys? Yeah? Exponential, I would agree with that. Okay, so if here's my xy axis, exponential function looks like this. There's an asymptote right there, and it curves up. You think it looks like that, sort of? Yeah, it looks like it would fit that kind of equation better than just a straight line, doesn't it? So, exponential. The general form of this equation, way back Algebra 2, we said a times b raised to the x power. So sometimes, to make it look like a straight line, we will not use the linear, but we'll use an exponential. Okay, now let's see. Do you remember what the inverse of the exponential function is? Good. Good. The logarithms. Yummy. You remember those logarithms? No. Logarithms have a vertical asymptote right here, and they curve like this. Yeah? No? Yeah. To be inverses, remember they're symmetrical along the y equals x axis. If you fold along that diagonal line, they would match, right? So the inverse of the function is a logarithm. Okay? So we're going to look at those two and how do we use those to make our data fit, all right? Looking at the data right here. So if we were putting this in our calculators, we're not going to take time to do it because you're never going to have to do it, okay? They're going to give you these outputs. But so here is this is what we would put in list 1 is the year. Notice they took the 2000 off. It was 2007, 2008. They just listed it as 7, 8, 9, 10, right? So that's my x value. This is my y value. So L2. So now what we're going to do is use the logarithm of the units sold. Take the logarithm of the y value and see if we can make a straight line out of that. So what we would do is take L3 and we would define it in our calculators as the log of L2. And it would then generate all the values for you. You don't have to individually calculate them. All right? So when I do that, I get 0.23 here, 0.95 here, and a 1 right there. So now here's my scatter plot. So my x's stayed the same, right? The years after 2000, but my y-axis would need a new label. It would be the logarithm of the units sold. Okay? The logarithm of the units sold. Not just the number of units sold, but the logarithm of that number. Now, I would use this in my calculator. I could calculate this, right? I could find the least square regression line doing that stat calc thing, right? Where x is L1, but this time y would be L3, right? So to save us a moment, I'll tell you what it comes out to be. Predicted log of units sold. So I need a longer hat on that. Comes out to be negative 1.54 plus 0.18, and that would be years after 2000. Okie dokie. How to do the logarithm? Go up to highlight the L3, highlight that, and hit log, and then second 2. And then it should fill in the gaps for you. Okay. Now, that being said, if we ran the residual plot for this relationship, based on this and the new r value, r squared value, so my r squared now, let me tell you this, is 0.97. So based on that and my residual plot, is this model better? Yeah, because why? What would you say? Yes, okay, there's no leftover pattern. And the r square value increased, right? Both are indicators of a better fit. Okay, so we're saying this model is good. So then it says, according to this new model, how many iPhones should be sold in 2015? So we're going to put it in this logarithm equation. We're going to say the log of units sold equal to negative 1.54 plus 0.18. What am I putting in for the year after 2015? Or 2000. I would put in 15. I said it wrong. Put in 15 here. I get 1.16. Is that my answer? Because really this is the log of the units sold is 1.16. How do we solve it? Do you remember this? Yeah, if you had me, we talked about swirling it out, remember? What was the base right there that's really tiny? You can't see it with the human eye. It's 10. See? Right here. 10. It's in there. Little baby 10. Okay? So when we swirled it out back in the day, we would have written it as 10 to the 1.16 power, which we can find in our calculators. Now, it could have been, could it be the natural log? You could have written it as the natural log, but then the base would have been e. But it still works. Okay? Don't work. All right, so when I do this, I get, what, 14.45, but I have to remember that the units is millions. Million units sold. Not just the number of units. That's not how much money they made on each one. Can you imagine?
And that was in 2015.
Now it was way back in 2015. Exactly.
We were so primitive then.
Right? Now, so that's really not that different than what we're doing, right? It's just a prediction question. Just got to use the right equation. Now it says calculate and interpret the residual for the actual number of phones sold in 2015. So how do we do residual? Actual minus predicted. How are we going to find actual? In the table. So the actual in 2015 was 13. minus the predicted, which we just calculated. 14.45 gives me a negative 1.45. Now I need to interpret. So let's say the actual number of iPhones sold in 2015 was 1.45 million below the predicted value. Can you live with that? It's not that different, is it? It's just showing you that instead of just a nice y equals x line, we can do some variations on that. All right? Can I turn the page? All right, so let's summarize this for a sec. Transformations. Okay, the first one, the one we've spent all our time, is just the linear. So that's just y versus x equation. Basic. Y to the first power, x to the first power, right? The exponential is what we just did. It's the logarithm of y versus x. What we call the power model is where you take the log of y and x. There are so many others. We could do a quadratic, we could do a cubic, we could do a square root, we could do a cube root. We could go on for days, right? We don't necessarily have to have names for them, but do you see that there's a lot of variation in here that could happen? The thing is, you're not going to have to calculate them. They're going to give you outputs like they did down here, and they're going to give you the scatter plots and the residual plots and all the things, and you're just going to have to evaluate which one is the best fit based on what we know. So when you do a prediction, like always, you're going to plug in x and solve it for y. When you solve for y, you might need to undo a root. What does that mean? Well, if it's y squared, undoing a root is just a square root, right? Or if it was cubed, it's a cube root, or a fourth root, or a fifth root, right? Or a logarithm. Remember, log is base 10. ln has a base of e. And then how do we determine good models? Okay, I'm going to give it to you in the list of priority things we check. Okay, the first thing, you check your residual plot. You're looking for no pattern. Second thing I would look for is a high r squared value. High compared to the other options you have, okay? And the third, now think about this for a moment. I don't want to give it away, but look at your table of stuff down here that we get typically. What else in here could be an indicator that the line is a good fit? We've done r squared. We're not really messing with all of this stuff in this lesson. What else could be a sign that this is a really good fit? Well, in this case, height is our slope. This is the slope of the line, and this is the y-intercept of the line. Standard deviation. And what is it the standard deviation of? Good, yeah, it's the standard deviation of the residual. So if that value is low, that means those points are really close to the actual line, isn't it? So it's a really good fit. So the third thing is the S value is low. All right? And that's it. Now these problems, although they are easy, they take up a lot of real estate on your paper. Because you got scatter plots, you got residual plots, you've got graphs, and a lot of times they'll say, okay, here's one version, here's another version, here's another one. Which one's the best one? And you have to look at all those graphs and charts and crap to see which one fits the best. And then you make a decision, okay? So don't let the fact that it might take 2 pages to ask you a question startle you because it's just charts and graphs, all right? So let's look at this example. It says the party company specializes in creating balloon boxes, which are boxes that are completely filled with small balloons. The number of balloons needed to create a balloon box is a function of the box height. Here's a scatter plot showing the number of balloons needed to fill the boxes of various heights. Note the clear curved form. You see that? Because height is one-dimensional and the number of balloons needed to fill the box, which is volume, is three-dimensional. Y'all remember that from geometry? Volume is length times width times height, so it's 3D, three-dimensional. I know you blocked it out, but here it is. This should describe the relationship. Here it is, what they're trying to tell us. Should describe the relationship. The number of balloons should be a function of the height cubed. All right? Should describe the relationship. Here is a scatter plot of the number of balloons versus the height cubed. So this one down here is that scatter plot. Does it look straighter to you?
Yeah.
A lot straighter, okay? Okay, because this transformation made it roughly linear, we use computer software to perform a linear regression analysis where y is the number of balloons versus x is the height cubed, okay? So there's my output. A just says give the equation of the least squared regression line. Define the variables used. So what are we predicting in this question? Number of balloons needed in these boxes. Okay. So as I read my table, I put my y-intercept first, 45.008 plus 10.809. And this would be my x variable is height cubed. All right, so if you didn't catch it when you read it, notice in the table it says height with a little caret cubed. So that's giving you a hint that that's the way it should read in your equation also. All right, and this is where you would look, like if this was the logarithm of x and the logarithm of y, it would say the logarithm of the constant, logarithm of whatever. This is where you're going to know what the equation should look like. If you can't figure it out from the wording, look in your table. Okay? Now, that being said, suppose you want to fill a box with a height of 8 feet. All right? Use the model from part A to predict the number of balloons that would be needed. Okay, a box of 8 feet tall. That's a really tall box, isn't it? It's a lot of balloons, so we won't be surprised then if there's a large number involved here, right? So let's plug that in. 8 cubed. It's going to predict the number of balloons. So when I number crunch all that, I get 5,579.2 balloons. I've probably rounded up to 5580, right? As long as the box can handle it.